The next NMR feature that we're going to look at is the integration. And the integration refers to basically the area of an NMR signal. And it tells us how many hydrogens that the signal corresponds to. So let's look at an example compound. Here we have chloroethane. And you should already recognize that there's two distinct proton types in the molecule, so you would expect two different NMR signals. But each of those signals are representing a different number of hydrogen. The signal for peak A will correspond to 2 hydrogen. The signal for peak B is the methyl group, so that will correspond to 3 hydrogen. So you would expect for the area of each signal to be in a 2:3 ratio. And on the NMR spectrum, you're generally given integration values above each peak. Now, in some cases, it will be very simplified in terms of having the exact number of hydrogens, but in other cases with experimental spectra, we'll have to do a little bit of work to figure out the true integration values, and that's what we're going to work on toward the end of this section. Let's look at a couple simple examples in the corresponding NMR spectra. So we'll start with this ketone right here, and you can see that this compound has 3 distinct types of hydrogen. We have first a CH3 group, so that signal should integrate for and represent 3 hydrogen. We have a CH2 group, and that should integrate for and represent 2 hydrogen. And then we have another CH3 group that is different than the first, and this should also integrate for 3 hydrogen. Now, if we take a look at the corresponding spectrum, we can see that our first signal here that's most downfilled is the CH2, and that integrates for 2 hydrogen. So that's why we have the 2H written over that, and that corresponds to this signal. And then next we have an integration for 3 hydrogen that represents a CH3 group. And this singlet happens to be this hydrogen right here, the methyl group on the ketone. And then finally we have another 3 hydrogen integration, and that represents the other CH3 group. So there's a 3 hydrogen integration, and that corresponds to this CH3. You see these integral signals on each peak, and these measure the area of that particular signal. And based on the area of the signal, the corresponding height of this integral will change. So you can see that the integration for the 3 hydrogen integral is taller than the one for the 2 hydrogen, and that's because this peak has a larger overall area. In the next molecule, we have this ether, which has symmetry that runs through it. So remember, you have this symmetry plane, and the 2 CH2 groups are equivalent, and the 2 CH3 groups are equivalent. So if we want to label these, here's a CH3 group. That will be signal A, but this CH3 group is equivalent, so that would also be signal A. And likewise for the CH2 group, we would have both corresponding to signal B. So then our integration for proton type A, we have 3 hydrogen plus 3 hydrogen. That's a total of 6 hydrogen. Then our integration for proton type B will be 2 hydrogen plus 2 hydrogen. That's 4 hydrogen. So now if we look at the NMR spectrum on the right, you can see that we have for proton type B an integration for 4 hydrogen, for proton type A an integration for 6 hydrogen. Now in this case, the integration numbers written directly above the signal exactly correspond to the number of protons that they represent. Experimentally, that's not always going to be the case, so we'll have to do a little bit of work to get the most accurate integration values. So now, keeping in mind the definition of integration that the area under an NMR signal is proportional to the number of protons that signal corresponds to, we're going to look at some different cases that you might encounter and how to work with those to generate the integration values. So in this first case, the integration values accurately represent the number of hydrogens. So this is the easiest case, and what we see is that in our molecule, if you were to add up all of the hydrogen, we have 3 plus 2, that's 5, plus 1, that's a total of 6. And then if you add up the integration numbers for your signals, we have 3 plus 2 plus 1, that's 6. If that's the case, then your integration values accurately represent the number of hydrogens, and it makes things quite easy. The 1 hydrogen integration in green corresponds to this hydrogen right here. The 2 hydrogen integration in red corresponds to this CH2 signal, and then the 3 hydrogen integration in blue corresponds to the CH3. In this second case, you're given whole number integration values like 1H and 3H, but they don't integrate for enough total hydrogen. So let's even assume you don't know what the structure is, but maybe from some other data you have the molecular formula. And we know that we need a total of 12 hydrogen. Well, if you add up the number of hydrogen in the spectrum, we have 1 hydrogen plus 3 hydrogen. This spectrum only integrates for 4 hydrogen right now. So what you need to do in that case is find a number to multiply it by to get to the total number of hydrogen, which in this case is 12. So 4 times what equals 12? That would be 3. So then you know that you need to multiply each of these numbers by 3 to get the true integration values. So we multiply this by 3, and this signal then integrates for 3 hydrogen. We multiply this value by 3, and this signal integrates for 9 hydrogen. And then that makes sense now if we look at the structure, because our integration for the 3 hydrogen right here corresponds to this methyl group, the CH3. Our integration for 9 hydrogen corresponds to these 3 equivalent methyl groups. In this next case, you may be given 1 or more integration values that are less than 1. And this is really common if you take an NMR spectrum and just have the computer set the integration values. It's going to give you kind of wonky values like this that initially don't make a ton of sense. If you have this, though, it's pretty easy to normalize these. What you want to do is find your lowest total integration value, and in this case, it's the one at 0.153, and then divide every integration by that lowest number, and that will normalize it. So let's divide each of these by 0.153. Right, the first one is easy, that gets you to 1. The second one, when we divide that out, that gets us to 1.5. And the third one also gives us 1.5. So we can't have half of a proton, so we know these values still aren't where we need them to be. And if you have an integration for 1.5, in most cases, you're just going to multiply that by 2 to get it to 3. The other way you could do this is just the way we did before and say we need a total number of hydrogen equal to 8 based on the molecular formula. Right now, our integration values, if we add up 1.5 plus 1.5 plus 1, that's a total of 4. We need 8, so 4 times what gives us 8, and that would be 2. So all of these values need to be multiplied by 2. So this first one, the final integration is for 2 hydrogen. The second one, the final integration is for 3 hydrogen, and then the third one, the final integration is for 3 hydrogen. And now if you add these up, 3 plus 3 plus 2, we get 8 hydrogen, which is what we need to account for. This next case is very similar to the last, where we have integration values that we need to normalize. In this case, instead of really small numbers, we have really large numbers. But it's the same basic process. What you want to do is find the smallest value, which in this case is 1475, and divide all of these by that number. So go through and do the math. This first one that we did, of course, is easy. That just equals 1. The second one here, the most downfield signal, divide that out, we get 2. The third one, we get 3. And then the fourth one, we get 5.99, which rounds up to 6. And just keep in mind, as you're doing these, you may not get exactly 2 and 3. You might get 2.1 or 2.2, which you would round down to 2. Or if you got 2.8 or 2.9, you would round up to 3. So even if your values don't come out perfectly, you round them to get the integer values. Now, in this case, we need a total of 12 hydrogen. And if we add up our integration values, 6 plus 3 plus 2 plus 1, those add up to 12. So in this one step, we were able to get our accurate integration values. This fifth case is becoming increasingly less common, but it's still important to know how to do. You could be given a spectrum where just the integral signals are printed on the spectrum. And from there, you have to figure out the integrations. And the way you can do that is by measuring the height of the integrals, because the height represents the area of each signal. So with that, you would use a ruler. So here I've overlaid a ruler on each of these signals, and we can see that we set the bottom of the ruler at the bottom of the integral for 0, and then measure up. So this first one corresponds to a height of 40 millimeters. The second one corresponds to a height of about 40 millimeters. And the third one corresponds to a height of about 60 millimeters. And this gives us our peak ratio. Now what you can do is probably deduce what these peaks represent. But if it's easier, you can use the same process we used in the last examples by dividing each by the lowest number. So our lowest number is 40. So if we divide each of these by 40, that will allow us to normalize our integration values. So this will correspond to 1, 1, and 1.5. We need 7 hydrogen total. So now if we multiply each of these values by 2, that will give us the correct total number of hydrogen. So multiply that by 2. This signal integrates for 2 hydrogen. Multiply the second one by 2. This signal will integrate for 2 hydrogen. Multiply the third one by 2. And this signal integrates for 3 hydrogen. Double check your work. 3 plus 2 plus 2 adds up to 7. So we do have the correct integration numbers now. One final case, which is very similar to the last, is you could be given a spectrum with these stepped integrals on it instead of individual integrals, but it really works the same way, where you just take the height of each section to tell you the area of the peak. So this one, instead of using a ruler, let's just see a way that we can probably eyeball this to make it a little bit simpler. And what you want to do is find your smallest step, and that would be this one right here. And we'll set that one equal to 1. And that means, for now, we're going to say the integration for this signal is 1 hydrogen. Now, if we move over to the integral to the left of this one, and eyeball the distances here, from here to here, that looks to be about double the last one. So from there, we can say that this would be an integration for 2 hydrogen. And then the height of this particular integral here looks to be the same as the height of the integral here with the most downfilled signal. So for that reason, this one will also integrate for 2 hydrogen. And then finally, we have our most upfilled signal. And this one, you can reason it in relationship to our first one here, and it looks to be about 6 times that height. Or it might even be easier to say, okay, here's the height of my 2 hydrogen integration, and it looks like I can fit about 3 of those 2 hydrogen integrations in there, so that would be a total of 6 hydrogen. Or if you want to split it up, it looks to be about 6 times the height of this first one here. So that's a 6 hydrogen integration. In this case, there's nothing more that we need to do. These values do accurately represent the hydrogens in this molecule. And just to help you keep track, let's label these. So we have our CH3 group type A right here. That corresponds to this signal. We have this CH, which is proton type B. That should have a 1 hydrogen integration. So that's our 1 hydrogen signal right here. We have a CH2C and CH2D. CH2C should be a little more upfilled than D because D is next to the BR. So I'll make D here and C here.